So that's going to tell you what concentration of ammonia you have present at equilibrium. Also, guys, pay attention. Your KQ is 10 to the negative 5. Is that going to be a product favored or reactant favored system? It's going to be a reactant favored system, which means this number better be a lot bigger than the reactants or better smaller than the reactants?
Smaller.
Better be a lot smaller than the reactants. Okay. The KQ tells us it's a reactant favored system, so that means our numerator better be a lot smaller than our denominator. And it is. If you got an answer, give me a thumbs up. About a third of the class. Okay, take another 30 seconds. Bang on that calculator.
Alright, do you really want me to bang on it though?
No.
Okay.
It's just an expression.
13.
Okay. What did you get for the concentration at H3? 0.08?
Yeah.
If you got 0.006, is that what you got? If you got that, what you actually have in front of you is the NH3 squared. Remember, your concentration, so if you just set this numerator as X, you're going to come up with 0.006 something. The 0.008 is actually the concentration of the ammonia. So watch out for those squares. When in doubt, plug the numbers in, and actually don't even when in doubt, always plug the numbers in and check everything. Okay. So if you can see how it's 0.008, give me a, raise your hand, or give me a thumbs up. All right. 17 minutes. Are you ready to change gears? Give me a thumbs up. Ready to move on? Put your hand in the air and wave it around if you have questions. Okay. Okay. So let's go ahead and just walk through the math. Hey guys, I don't really want to talk over you. All right. So let's go ahead and walk through the math. This is going to be 1.5 times 10 to the negative 5 over equals 5.4, 2.9. So that means the NH3 squared is going to equal to 1.5 times 10 to the negative 5 multiplied by 5.4 cubed multiplied by 2.9. So that's going to give you a number, I don't know, it's 0.0. What is the actual number before you square root it? 0.0068?
Yeah.
Okay. And that is going to be that with squared. And then the NH3 is going to be the square root of that 0.0068. And that's in the neighborhood of 0.0083. Oh, sorry. 0.08 something. 0.08 something. 0.083? Feels like 3. Alright, cool. Okay, so how we doing? Should we move on? Muy bien. Sehr gut. Very good. Okay. Off we go. Alright, so solubility product. Solubility product is what you get to determine how many ions you can dissolve in solution. Let me give you an example. If you take sodium chloride, solid sodium chloride, and you dump it into water, what's that sodium chloride going to do? Starts with a D and ends in ol. It's going to dissolve. And it's going to dissolve into what two things? Sodium, ion, and chlorine ion. So, are we wasting time?
No.
Okay. So we're going to dissolve our sodium chloride into a sodium ion and a chlorine ion. Now, we have a special K called a KSP. KSP stands for solubility constant, or solubility product. So this is going to be just like the equilibrium expression, products over reactants. What's the product in my KSP equation? Yep. Concentration of Na plus, and what else? Concentration of the chlorine, right. And what else? Over nothing. Because remember, solids don't show up in the equilibrium expression. So it's over nothing. There's no solids, or there's nothing but solids as a reactant. Okay. Can you see how that makes sense? You understand why we don't put the sodium chloride in there?
Is that so?
Because it's solid.
Is that just one?
Yeah, it's like over one. Yeah, it's like over one. So the KSP is how many ions can be dissolved in the solution in equilibrium with its solid. In other words, how many ions you can get into solution before it becomes saturated. We did saturation last week. I'm going to say last week because remember that. Yeah. So we did the equilibrium where the solid is in equilibrium with the ions floating above it. That's saturation. So the KSP is how many ions you have at saturation. So this is an example of silver chloride. If you try to put silver chloride in solution, you dump some silver chloride in solution, you're going to get a saturated solution pretty quickly where the silver chloride is going to break into silver and chlorine. And once you've satisfied the KSP, no more silver chloride will dissolve. So once the silver ion multiplied by the chlorine ion equals 1.8 times 10 to the negative 10, no more silver chloride type will dissolve. That's what the KSP means. Does that make sense? Now, this is great. If you wanted to solve for this, you can realize, I'm kind of going fast because we only have like 12 minutes left, but for every one silver chloride, how many silvers do you get? One. How many chlorines do you get? One. So if the concentration of silver was X, what's the concentration of chlorine? Also X. Because it's a one-to-one relationship. For every silver you get one chlorine. So if the concentration of silver is X, then the concentration of the chlorine would also be X. Okay, give me a thumbs up if you understand why that is. Okay, sure. Put your hand in the air and wave it around if you want me to go over it again.
Want me to just raise my hand?
No. No. If someone has a question and they don't have the guts to answer it, then that's all on them. So I'm here for you. If you're like, I am shy, then you can be shy dropping out of school. You can be shy at community college. The rest of us will go to a big state school and be successful.
I'm going to Yale.
You can go to Yale.
No, I'm kidding. I'm going to go to SU.
You're gonna go to Duke. All right.
I wish, dude. That'd be.
Dude, yeah, Duke, man. All right, so take a look. This is the solubility product constant for calcium fluoride. Can you see the differences between calcium fluoride and silver chloride?
Both.
What do you immediately notice about the two?
It's 1, 2. Extra water.
Yeah. You immediately notice that for every calcium fluoride, you get one calcium, but how many fluorines do you get? 2. Are you paying attention? That means for every X calciums, how many fluorines do you get? You get 2X fluorines. Does that make sense? Okay, so calcium fluoride breaks down to a single calcium, but 2 fluorines. So that means for every calcium you get, you're going to get 2 fluorines. For every X calciums, you're going to get 2X fluorines. Question?
So it's not squared, or it's not like an exponent?
It will be squared in the equation up here. Yeah, this squared from the equilibrium expression will still exist, but the 2x there is what we care about at this point in time. that you just realize that since you got 1 calcium for every calcium fluoride, 2 fluorines for every calcium fluoride, whatever concentration of calcium you have, the fluorine is going to be twice that. Cool? Thumbs up if you're cool. Wave your hand around if you're not.
Be cool.
Be cool, dog. Okay.
Dog.
Dog. All right, cool. Now, moving on. Right. Leia, hold me. Q. Q is the concentration of ions at any point in time. I'm going to back that up a little bit. Q is the concentration of ions at any point in time. So, Anthony says, I got some salt, I got some water, I'm going to pour my salt into the water. And I'm going to go tap, tap, tap. Okay?
Oh, wow.
Just like in the simulation, it's going to start dissolving. Initially, is it saturated? No, it's not saturated, but it is most likely unsaturated. Which means the amount of ions I have in my beaker are less than what they could be. That's what saturation means, right?
Yes.
At a saturation point, you have as many ions as you could possibly have. That Q is what you have at any point in time. The Q is what you have at any point in time. So if you think about that, if you have a QSP, that's the concentration of the ions, that is less than the KSP, with your finger or your thumb, is it unsaturated, saturated, or supersaturated? Is it unsaturated? Is it saturated? Is it supersaturated? When the KSP is less than when the QSP is less than the KSP. Most of you understand it is unsaturated. There are fewer ions than the KSP says you can have. Does that make sense? Now, if the QSP is equal to the KSP, then what is it?
Saturated.
Then it's saturated. And if the QSP is larger than the KSP, then it's supersaturated. So I just have that up here to remind me. When the QSP is larger than the KSP, it's supersaturated. And when the QSP is equal to the KSP, it's saturated. That's what the QSP means. It means at any point in time, the beaker in front of you, how does it compare to the overall saturation limit? If the QSP is equal to the KSP, it's saturated. If the QSP is less than the KSP, it's unsaturated. You could still add more ions. And if the QSP is larger than the KSP, it's supersaturated, and there's too many ions they want to get out. Cool? Okay, give me thumbs up if that makes sense to you. All right. Okay, math. Here comes some math. Watch out, it's math. Okay, this is what we're going to be practicing this week. Actual examples of exercises you're going to encounter. The question is, how much silver chloride will dissolve in 1 liter of water? We're going to use the information we have to figure out how much silver chloride will dissolve in 1 liter of water. So the first thing we have to realize is the KSP at saturation, because what we really want to know is how much can we add until it becomes saturated, right? So the KSP at saturation is 1.8 times 10 to the negative 10. And that equals the concentration of the silver multiplied by the concentration of the chlorine. So far so good? Okay. Next. We know that for every silver, there's how many chlorines? 1. So that means if you have X concentration silver, you have X concentration chlorine. Solve for X. What is the concentration of the silver chloride going to be? What is the concentration of the silver chloride going to be? Or what is the concentration of the silver going to be? What is the concentration of the chlorine going to be? Then work backwards. I'm hoping it's going to be times 10 to the negative 5 because you're taking a square root. What'd you get? 1.34 times 10 to the negative 5?
Yeah.
Okay. And that's going to be molar. And your calculator might have spit it out this way. 134 molar. Your calculator might have spit it out without scientific notation. So 10 to the negative 5 is going to have 4 zeros. 10 to the negative 3 has 2 zeros. 10 to the negative 12 has 11 zeros. 10 to the negative 15,000 has 14,999 zeros. Okay, cool. So this is the concentration of silver and chlorine and what?
I don't know, water, what?
Remember, it's a 1-to-1 ratio. Every time you have one of these, you're going to have one of these, but it came from this. So this is the concentration of silver and chlorine and silver chloride. That is the concentration of silver and chlorine and silver chloride. Hang in there, Tony. You can do it. I believe you. It's like, I was staying up late watching reruns of shows I don't care about.
So basically, we're trying to find
I want to find the number of grams. So what I've got so far is the concentration of silver chloride is equal to 1.34 times 10 to the minus 5 molar. And it says I'm going to dissolve it in 1 molar of water, which is great because molarity is just mole over liter. So how many moles of silver chloride do you have?
one.
No, not one, but
I mean, yeah.
some people can do this in their head. Over 1 mole or 1 liter. Yeah. You've got 1.34 times 10 to the negative 5 moles of silver chloride, and then you do a T-chart and you will have grams of silver chloride, and that's where we're going to end. For every 1 mole of silver chloride, there's going to be so many grams of silver chloride. And while you work, I'm going to kill the camera, and we can finish this up.